I think that the smartest career move I ever made was to come spend a year here, actually. Not only getting 8 time zones away from my dean so I could get writing done, but the year that I was here, 2004, 2005, was just as the e-science was really taking off. It's when, in fact, I met Tony Hay upstairs. That was our first meeting in that little conference room with Tony and with Ann that got a lot of that moving. And it was, we went to, actually Ralph and I went to the launch of the E-Social Science Center that year, and I was up at Edinburgh for the opening of the Digital Curation Center. And then that opened just a whole lot of doors, so that the ability to do the kind of comparative work was just such a pleasure to be here. And the collaborations continue, and Marina's and Eric are part of some of our projects, so we're trying to move forward as well, too. So with that, this is the book that started right here in this room. Actually, the first talks, the first kind of preview, you folks really helped me think through a lot of the problems that this came out to be. What the Open University is asking for, and this is the title here, this Making Connections Conference, Exploring Scholarship for the Digital Age. Brenda Gurley, their vice chancellor, sort of set this off and said the theme for the 40th year of the Open University, they started in 1969, this is actually their 40th anniversary, should be scholarship in the digital age. And she quoted very heavily from the book, and then they asked me to come and keynote it. So what Americans have to say to Open University, I'm still trying to figure out, because I think Open University understands the issues of open learning and distributed learning better than most anyone else, certainly on our side of the Atlantic does. So what I want to do is kind of work through a big picture, because I think what this notion of blurring the boundaries between research and learning is where e-science and cyber infrastructure are really going now or going next. So see if you can bear with me on some of this, and I hope I'll provoke for plenty of discussions. So infrastructure, what do we mean? I mean, a number of us in this room study infrastructure in great depth. To a lot of people, it means things like roads and bridges. It also means lots of plumbing and pipes, like this stuff from state of Texas. It usually means things like telecommunications infrastructure and satellites. I particularly like this one from the U.S. Department of Commerce. So there's our shipping lanes as infrastructure. But this one is probably the best sense of where we are with infrastructure for scholarship at this stage. Because here we're trying to build this bridge, but we've got what looks like a Roman aqueduct back here. Okay. So it's how are we going to tie all these pieces together? The Roman aqueduct is still going to be there, but we're trying to build something very new. And this is the time to keep thinking about what we could build, what we should build, and what the motivations are for all of it. So, scholarly information infrastructure, cyber infrastructure is the term we tend to use in the U.S. And as Marina and Ann and Dave and I were talking earlier today, there's still quite a bit of moving back and forth as to whether we use e-research collectively, which is what you've chosen to use here, or divided up by the different kinds of areas and centers. And I think the humanities, which we'll come back to, are very much in their ascendancy in this arena as well. All of them mean some combination of these things, whether we're trying to build some new kind of scholarship that's more information and data intensive, is more distributed, collaborative, and crosses disciplines in new ways. And I'm going to focus mostly on the data. And I think the data are, as Paul said in one of the earlier reports on e-science, the third stream of scholarly capital. We've really moved beyond just thinking of the publications as the sole output. We're really thinking of data in new ways. But data is much of what gets distributed. It's much of what we collaborate about. And that's why it's a good way to think about what some of those relationships might be. Okay. This is a slide that I borrowed from Ian Foster of the Grid that most of you probably know. He used this in February at the AAAS meeting to talk about our moving into a fourth paradigm of thinking about how science is done. So if you think of Aristotle as the empirical method, Leibniz bring us into theory, John von Neumann into simulation, and Jim Gray, the late great Jim Gray, the Turing Award winner, of moving us into notions of data as a new method or a new paradigm of science. And it's this great trajectory, but it's new ways of thinking about what we can actually do, what new questions we can ask if we have these kinds of data. This is a quote that Ian provided also from George Jergovsky from Caltech, who is also active in the eScience area, and they organized an eScience meeting a couple of years ago at Caltech. He's saying that applied computer science is playing the role that mathematics did from the 17th to 20th centuries. The analogy is useful as far as it goes, but probably what's different is that mathematics was known as the handmaiden of the sciences, the set of tools. Computer scientists get very upset if you use that kind of analogy. It's much more of a kind of partnership. This is one of the real challenges as we get into particularly the multidisciplinary and collaborative work, is finding problems that are of mutual interest. When you match up the biologist or the chemist or the art history professor with the computer scientist, finding something that each of them can publish in their own domain continues to be one of the difficult parts. So I think that's one of the things I'll try to highlight as we go through this. Okay. Liz Lyon's report from 2007, I'm sure most of you know, the Dealing with Data, Roles, Rights, Responsibilities, and Relationships. I tossed that into Wordle. And this tag cloud is kind of nice because, I mean, obviously data jumps right out at you. But research is in here, and then deposit, access, curation, management, repositories, preservation. These are the kinds of things that come on around it. So I think that's a nice little snapshot of the sort of relationships when we think about roles and responsibilities and such with data. Similarly, this is courtesy of Alex Zale, who is the founding PI of both the Sloan Digital Sky Survey and the Virtual Observatory of Astronomy. I put this slide in to show not only the sheer size, and Panstarrs is the next technology that's coming online after Sloan. Sloan is now closing down after, I think, 10, 15 years of data collection and becoming an archival project, figuring out just how to archive the Sloan Digital Sky Survey as a challenge. Panstarrs already has about 20 times as much data as were collected in all of the Sloan Digital Sky Survey. This is now pushing the edge of computer science research, and they're looking at grid issues about when you move the data to the computation and when you move the computation to the data. So different kinds of distribution and collaboration are coming up here. This one also from Alex, I think is important for several reasons. One is that little science, which is a lot of what we do in SENS, of people out in the field sticking sensors around the world, is becoming more big science as they get greater data volumes. These are figures just from the Long-Term Ecological Research Center Reserve outside Baltimore. They are looking at carbon dioxide emission in soil, 20 million measurements per year of just carbon dioxide in soil. So we're really ramping up the amount of data that small science is using. Another point to take away from this is the multidisciplinary. The Sky Server data from the Sloan Digital Sky Survey is being used to model the data in soil emissions. So people are starting to transfer the technologies between disciplines. Victoria saw this a couple of weeks ago at Harvard because that talk was sponsored by the Initiative in Innovative Computing. This is one of their best-known projects. And what's important about this is, again, that transfer of technologies and partnerships between disciplines. They have taken research from medicine in brain science, where they take CAT scans and MRIs, which are two-dimensional images of the brain, and then they use them to turn them into 3D models. That technology is now being poured over to astronomy, where they're taking 2D images of stars and turning them into 3D volumetric images. So you've got a crossover of disciplines, and you've got some very sophisticated computer scientists working with these groups. And then you've also got this incubator environment, this initiative in innovative computing to get these people together under one roof. I know I showed this slide on your previous technology that was here, but perhaps to make a different point. This is a still shot from Rome Reborn, which started at UCLA and is now joint between University of California and University of Virginia, because Bernie Frischer is now the head of Advanced Technology and Humanities at Virginia, and so took the project with him. This is interesting for several reasons. One is it's multidisciplinary collaboration. You've got people from classics, from archaeology, from architecture and computer science, all working together on it. And I participated in some of the early work where they're trying to come up with the metadata models, and realized that one group was trying to move through this from architectural periods, and another was trying to move through it from political periods. But until you get kind of an outsider to look at it, you don't realize that they have varying notions of sort of what's important behind this. There's a lot of scholarship behind it. It hooks into a bunch of different bibliographic sources that shows you why they thought it was a temple at one time and why they thought it was a marketplace at another, and how it changed. There's overlays to do teaching with it, and it's now being used as a tourist attraction in Rome. You can go take a 3D walkthrough with monks talking Latin in the background. But they're also come up against the digital archiving, and that was also part of our lunch discussion with David around when do you archive sort of the underlying data sets, and when do you try to archive the whole thing that moves is something else, and that's so how do you save virtual environments is one of the things that Bernie's group is trying to deal with there at Virginia now. Okay. Which takes us back to the question that plagues or intrigues me, and intrigues I know Marina and Ralph and others, is just what do we mean by data in this environment? In a lot of those documents around e-science, you tend to see assumptions that suggest that the data are objective facts, that they're observations, something that you can touch. And so when we say who's going to archive them, will the library take them? Well, will the investigator take them? There's an assumption we know what the it is, when in fact we really don't. And this is the punchiest one, I always like from Michael Buckland, is simply to say that the data are alleged evidence, that they don't become data until someone makes a claim about something. I had was really challenged by a high-energy physicist at a recent talk who said, data are data, an observation is an observation. And if you'll bear with me through some of the SENS examples, I'll continue to argue that an observation of one investigator is not the same as an observation from another investigator. So deciding what it is you want to capture, what you're collaborating about, and what needs to be saved is one of the harder challenges for us. Okay. So now I want to give some comparisons of how these things are playing out across the sciences, the social sciences, and the humanities. This was chapter 6 that Ralph and I spent a good bit of time. I bought a bunch of beers to people on multiple occasions to help me kind of work through some of these problems of the differences between disciplines. Thank you. Right. Learned at Oxford. You see. So I'm trying to make two contrasts here, one on the example side of the slide and one on the sources side. So on the example slide, the point is that individual fields have many different things that they consider to be data, and that's, of course, a very tiny subset, just one or two examples from each of several disciplines. Here, the point being, in the sciences, people either generate their own data, or else they tend to get data from other sources that were generated for scientific purposes. Okay. And again, the Sloan survey is a nice example for several reasons. I think Sloan is important because of this kind of value chain idea, where they are one of the few that explicitly hooks the publications that came from it to the data itself. More than 1,700 scholarly publications came out of the Sloan Digital Sky Survey. And so you can search this set for the publications, you can go to the data set, you can search the data sets, you can go to the publications. Another reason it's important is it really opened up the notion of open data in astronomy. Astronomers were as bad as anybody in terms of locking down their data, not sharing. If you got money from Keck, it was yours. And what Sloan did is says, if you give us the money to do this, everyone will have the data. And the investigators were supposed to have a short embargo on it, but it took them so long to get it released, they actually didn't even really get their embargo on it. Okay. And then the third is it's important for learning, because it turns out the vast majority of uses of Sloan were not by astronomers. It was very popular for citizen science, for teaching. A number of other discoveries were made from it. And then there's this overlay. I've got a slide farther down, the Galaxy Zoo, which actually the BBC was the one that released it. Anybody played Galaxy Zoo? A couple. Okay, so what Galaxy Zoo did was it invited you to classify galaxies by which way they spun. And it got so popular that it crashed the servers within a matter of hours after the BBC announced it to come play with it. So they ginned up the servers and made them much more sophisticated after that. But they got the data in a very short period of time of enough classifications to do it. Okay. In the social sciences, again, you've got lots of things that can be data. And the social sciences fall somewhere between the sciences and the humanities. Most social sciences do collect their own data, but some will get things like surveys from repositories, and then others will go to get census data, econometrics, and things that were not collected by and for research purposes. This is just one example of a social science data archive. This is the one at UCLA. There's the UK Data Service at Essex. The largest in the US and perhaps the oldest is the ICPSR at University of Michigan. Berkeley has a very large one. The one at Michigan has just announced a new program called Teaching with Data. In fact, it's teachingwithdata.org. And UCLA is a partner in this as well. They're trying to get the use of data directly into classrooms. And I think anybody else could participate if you want to play with particularly through the e-social science. I think that would be a nice one to partnership. It was just announced. I can send you a link to it, Marina, if you would like. So I think we're going to find that crossover there. The humanities, give your Beasley across the street archive. The humanities are the most distinct, I think, from the humanities and social sciences in at least two respects. One is that because any record of human experience can be considered data in the humanities, you don't have that distinction between what's a publication and what's data. You know, the Jane Austen novels, which were written to be read, can be data if you can do entity extraction on them, if that's your particular kind of research. But what that means is that humanists tend to generate very little data themselves. They're very reliant on intellectual property from other people. So their IP issues in terms of access and control and release and curation are much harder. So, do we just jump to conclusions like Chris Anderson and Wired Magazine did? I've taken this cover shot. Ian took this cover shot. I think it's a very popular cover shot because it annoyed so many of us when this came out about a year ago. There's a real concern, particularly people in Congress and Parliament may jump to the conclusion that all of the problems are solved, science becomes easy, the data are out there, they're objective facts, we know what to do with them. And it's great to have the data, but it raises a bunch of other problematic issues. And similarly, where are we now? I know Sarah knows what this is. Are there any non-librarians who know what this is? No? You know what the... It's the cover page of the Royal Society's first journal, and it's considered the first English language journal in the world. The French issued one within months of about the same time. So those are considered the first two scholarly journals. And what's intriguing about this is how little has changed. You've got your title, you've got your volume, you've got your date, you've got your statement of responsibility in the Savoy, printers to the Royal Society, and there's the same journal, which says the world's longest running international science journal. And you've got all the same data elements on it. that we had originally. So it's changed, and yet it hasn't. So this is one of the points that I want to make is a lot of the underlying functions we're just doing in a different way, particularly in the publication area, which has not really jumped as much forward, I think, as the data area. So this is just two quick slides of the history of publishing in one slide. This is chapter 4. Actually, sort of chapter 4 and chapter 5 for the comparisons. The reason scholars publish is first to legitimize their work, which in the print world we have done through peer review, to disseminate it, which was done by publishers, authors might do some of it, and then to access it, preserve it, and curate it, generally done by the library. This is our Neo-Gothic library, undergraduate at UCLA. For electronic journals, we're doing peer review a bit differently, but we're still doing peer review. Although it's surprising how many arguments you still have with people about whether electronic publishing is really publishing and has the same quality. But the fundamental difference is really the form it releases in. This quadrant is the biggest difference down here. Okay. Libraries are becoming even less visible, and good infrastructure is infrastructure you don't see. But as libraries are leasing access to materials rather than owning it, and publishers are holding things on their servers, you don't have the same kind of visibility of the institution, and this has become a much more diffuse set of responsibilities, and the lines between what's the publication and what is the informal has changed as well. Okay, so this is a deliberately forced comparison to data to show how immature we are in terms of the processes around data. We don't have much in the way of how we legitimize things, particularly if things appear in publications. And that still is largely how people find out about things. Marina, you were saying over lunch about the medical council and how they'd like people to come and ask them for a DVD or a CD, whatever, but that way they know who's got the data and they know where it came from, and there's a direct relationship between the provider as opposed to putting it into a publication. Only in a few fields, like mathematics, do you really work through the proof and verify it. People don't really go back. You know, there's a fair amount of just reputation in terms of quality checking. And the request to an author and local maintenance is more often the way the data are found. If it gets into a repository, it starts to look much more like the publication process. Because then you've got somebody who will look at the quality of metadata, will test drive it, which I think was something at Oak Ridge. So we always test drive the data. And you get notions like data that get used improve. You know, people will find problems with them and will feed it back in. You've got somebody disseminate it, and you've got some means for access to it and longer-term curation. Okay. So that's a reason we're pushing in this direction, but it's really pretty problematic to get there. Okay. So this is the short case study I promised, and this is the one we'd like to put a piece of in Marina's special issue of Journal of Computer Supported Cooperative Works. It gets into some of the very interesting data sharing and collaboration issues. This shot was taken in Bangladesh, where they were out looking at water contamination. Arsenic contamination in water and rice paddies is a real issue for them. And so this team was testing out some of our sensor network there. Nithya Ramanathan got her PhD from UCLA, specifically looking at the data quality from the sensor networks. Okay. Now, SENS has nearly 300 people involved by now. But about 2/3 or more of them are from computer science and engineering working together. And we're in areas of contaminant transport, seismology. A lot of the workers are right on the technology per se. So these are the kinds of things that we put out. This is a 3D robotic sensor that can move through space. And until they built this, they were stuck with kind of scaffolding in specific spaces. And this is the robo-duck, which is a robotic boat that goes out, and there's a little helicopter and other things that go out as well. But notice how we got sensors in lots of places and then a receiver, and then they talk to each other. Deborah Estrin, the head of the center, likes to say that the network is the center. The network is the sensor. By having much higher granularity of data collection, the comparison between the sites is as important as the individual measurements that they get from this. Now, these are some of the things that we're looking at. So SENS would like to share its data, big NSF Science Center. So we're asking questions about what are the data, how will they be shared, what do you need to know about them, the contextual information, and what metadata can you put around them. Then we're building systems to manage those data, and then we're trying to leverage those data for research and for learning. We have some of these data in middle school and high school classrooms being used to teach ecology. I have lots of examples. I keep using this one because you don't need a lot of context to understand what's going on with it. This is from one of the field deployments where we have biologists and engineers working together. This is a quote from one of the engineers. As soon as those sensors start beeping and sending signals, they think they've got data. Okay. Biologists on the same project. There's hundreds of ways to measure temperature. The stuff coming off the sensors does not meet the international standards. I need to know how it was calibrated. I need to know if it's above the tree, behind the tree, in the sun, outside of the sun. There's all these other things that I need to know about it before I can trust that. This group put up 3 different temperature sensors beside each other and let them run for 365 days before they trusted the temperature coming off it. So these are the kinds of notions about collaboration that you get into, and what are the data. Similarly, and I've used versions of this slide for various reasons too. Jillian Wallace drew this for us out of our team. When people say, what are the sensors coming off, what's the data coming off the project, they usually mean all this stuff here in the middle. Okay, so these are, and actually what's coming off the sensors is pretty much impedance and microvolts and so on, which they're then running through models to decide what is temperature and sap flow and water potential and leaf wetness and so on. The biologists are often setting up wet labs at the same time, and they're looking for mercury and so on, but they are literally dipping things out of water and putting chemicals in them and doing centrifuges in the field. They've, the one group doing beach quality has this down to something that will fit in a little red wagon that they can carry around with them for a wet lab. But they don't trust this until they have this as well. The people doing the robotics work for that robo-duck, they need the rudder angle and the motor speed because they're deciding where to go collect data next. And then the people like Nithia's group are concerned about battery life, neighbor tables, and packets, and so on. Okay. The first 3 years of SENS, the majority of papers were about battery life and not about data. I've been yammering about data since 2001 when we were writing the proposal for it, and nobody took me seriously and for about the first 3 years until there was enough data that people started getting concerned about it. These 4 sets of data get stored in at least 4 different places by the groups that collected them. So if you want to come back later and reconstruct the field study to be able to replicate it or to be able to reproduce it, the kinds of things Victoria's concerned about, you would need to put all these things back together again. On the current state of affairs, it's very difficult to put those back together again. And of course, the data exist in all kinds of different places, and they're really more concerned about backing it up than they are about curation per se. I mean, these people don't really, if you ask them about curation, it's usually like it's in my student's laptop and it's in the lab. And that's about as far as curation goes. Some of the people will say, yeah, you can have my raw data because I know you can't make any sense out of it. And the water quality people are very concerned about things like certification. But even the notion of certification doesn't mean anything to the seismologist, but it does the environmental sciences. Okay? And again, this is one center of people who have been working together for a very long time and have different notions of what the data are. Okay. So these are some of the things that our group is trying to do with it. This is a life cycle that we've identified, and you'll notice that this is fairly specific to this kind of research. They design an experiment, they calibrate their instruments, they go out in the field, capture some data, then they derive some measurements from it. They start to have to integrate things from multiple sensors and multiple data streams before they can do the analysis. Then they go into publication, and only then does preservation and curation become an issue. So we've got one set of technologies, digital libraries, trying to manage the data sets, although we will actually point to wherever they choose to put it. The deployment plans, this was done entirely within our group because the oral culture really started breaking down once we got over 100 people or so, and they were showing up at remote sites lacking a couple of cables or batteries and so on. And this has turned out to be very useful to capture things like that calibration data and link it back together again. And one of my students, working with some of the computer science students, has now been able to visualize that data quality through Google Earth and overlay it on the seismic array in Peru that they've done. Then the publications were loading into the UCE scholarship system, the UC repository, and then we're trying to label all of these with uniform resource identifiers so that we can do an overlay using the Object Reuse and Exchange Initiative to build the aggregations. So there's another whole other technology layer, and the technology layer is some of the things that Tony Hay is funding and helping us do this. Okay. So that's my case study. Let's kind of step back a bit to what about Chapter 8 that we had a lot of long hashes about why people would choose to share things. Well, there's obviously the notion of open science. I mean, it's not science, it's not scholarship until it's peer reviewed, until you're willing to release it to people. You want to get recognition for your work. You have to have something to collaborate about. You would reciprocate. But there's also coercion. And as funding agencies start to withhold the last payment on your grant until you've deposited the data, the incentive structure may change. One of the things that Alberto Pepe, my student that we got from CERN, did when he was doing digital library work there is they set up a system where CERN faculty and staff wouldn't get their reimbursement for traveling to present a paper until the paper was in the repository. It's certainly coercion, but it's a good way to implement the repository deposit. It worked for them. Okay. Okay, so we did this one. And then the incentive's not to share. Okay. We still get hired and promoted for publication. And we need people to do much more data management, but in very few fields do people really get credit for doing that or for building new kinds of genres. It's much harder to document the data for other people to use than it is to keep it for yourself. The priority of claims issues tends to be dealt with through embargo periods, where it seems to vary from anywhere from 6 months to 5 years that you get to keep control over your data before you release it to somebody else. And then lastly, the intellectual property problems. And I think the lack of clear definitions of data goes in that last category of it's not clear what it is going to be shared. The control of your own resources tends to be more of an issue in the sciences. Access to resources controlled by other people is more of an issue in the humanities. Okay. So that brings us around to open access, just briefly about kind of some of the tools and services that we're building. If e-science is really going to produce reproducible results, we need a way to make sure they get out there, they get licensed, they get controlled. Creative Commons licenses are getting very popular, particularly for repositories. The Science Commons groups that Victoria's also working with is doing some very sophisticated and interesting work on licensing and capture and reproducibility issues, and on provenance issues too, because that's one of the things is if you know who had the chain of custody, that's going to make a difference as well, and that's one of the things that they're doing some good things with. And I have pointed people to Sherpa Romeo at every opportunity. I think this is one of the best things that's come out of the e-science initiatives. Here is a way to check easily what your rights are, and by being able to check what your rights are in publications before you decide where to publish, that really changes the game. Because people tend to wait until the paper's been accepted before they think about their rights, by which time it's pretty hard to bargain. Okay. But if you choose up front, you're in a much better bargaining position. Okay. Openness Matters for a bunch of reasons. It's not just about undermining the publishers, although that's what some people would like to do. It's about the discoverability of different kinds of documents, different kinds of data, and research materials. If things are going to be usable and reusable for research or for learning, they need to be interoperable. You need to be able to import and export. You need to think much more in terms of Web 2.0 common platforms. And it's also Jonathan Zittrain's notion, more generative technologies, if you're going to be able to move across these different environments. Okay. Which brings us to this last project, another one that was initiated by Dan Adkins that I had the honor of chairing. This came out last summer. Just keyword search it. Don't bother with this horrible URL that they put on it. So a very interesting mix, and it was jointly commissioned by Cyberinfrastructure and Education Learning at NSF. And Malcolm Reed took my last copy of it from Educause. So I don't know how far things have gotten here, but he was very interested in trying to implement some of these things on this side of the pond. Cyber learning, what we mean by that is how do you build on that research infrastructure that we've constructed and use it for learning purposes. So it's not just learning about cyber infrastructure, it's learning with cyber infrastructure. But notice how you could really just put research where learning is here. I mean, that's a lot of what we're trying to do with eScience, is using networked computing and technologies to support research, collaborate over space, and use materials. And we're talking about K to gray, K being kindergarten. Okay. And then it's important because it's ways you can take advantage of the technologies that people already have and extend the capacity of educational institutions. And there's some very good statistics out there about the increasing demand for higher education, and an estimate by Sir John Daniels, who was previously head of Open University, that you would need to build a new university every week to build the demand that's expected in the next 10 years. That's obviously not going to happen. Okay. This is one of several recommendations that we made, was precisely around getting more data into learning at all levels. So if kids are really going to grow up doing computational thinking, moving into a place where they can be e-scientists, you would like them to get involved very early on. There's your Galaxy Zoo that I mentioned earlier. Okay. There's a lot of social science opportunities also in the data that gets thrown off from these e-learning systems as well. You can roll out technologies and test them on 300,000 students at once already, and some of the people in the U.S. are doing that. And Open University has, what, 220,000 students? I mean, it really is a matter of the scale that you can work at. But then you can feed back, you can adjust the learning, you can adjust what students learn, speed things up for some, and slow things down for others. Okay. How many of you have played with the Worldwide Telescope? Only you, Paul? It's really fabulous. It's actually, I think, a visible product of Tony Hay being there, of the more openness of Microsoft. This is being put out for free public use, so that's pretty important, interesting in and of itself. It's also important because it's this notion of seamless astronomy. They've already got 40 different data streams of astronomical data coming into it, and you're able to move across things like different wavelengths that would otherwise be in different repositories and move through them in a seamless way. So the computer science is pretty fabulous. That's behind it. It is multidisciplinary. It's got people in computer science, design, astronomy, and physics all involved in it. It's useful for the scientist as a viewer of data, but there's also overlays of learning that you can put on it, and you can go and take tours of the sky. You can pick your favorite object and go touring through it, and there's a great tour by a 6-year-old that's in there as well, and a couple of new discoveries have been made with this. Okay. Let me wrap up with 2 slides. One on the notion of there being a content layer to this infrastructure, the part that libraries and archives are particularly interested in, and how we can kind of tie it all together into a chain of related materials so we can really get that much more Web 2.0 seamless environment. Those 4 categories of data are the ones from the Long Live Data Report, but I think they're actually pretty constraining. I don't think they do us that much good as when we start to move over into humanities kinds of data. Lots of different kinds of publications, and even though you would certainly consider wikis and tweets to be somewhat ephemeral, that's also the way that people discover things. I mean, people are now tweeting about the new document you have to find over here, so it's not always clear you want to throw all that. Some of that's worth capturing. We've got lots of new kinds of genres, including these virtual cities and sky tours. Large amounts of learning objects and products and student work, individual and collaborative, that you may want to keep track of, and then composites of all of these things. So how do we think of all of these things as products of scholarship and products of learning that are worth capturing and worth curating and coming back to? And lastly, my favorite library slide picture. We've got both research and learning, I think, are becoming more information and data intensive. We can bring those together and look at both of them in that way. The scholarly practices around publication, peer review, refereeing, if you will, are much more stable than are the scholarly practices around data sharing. We've got a long way to go there. Learning activities are going to require much more access to all of these resources, but tools and services to exploit them. University practices, we're very concerned at UCLA with how we're going to build a scalable and sustainable infrastructure. It's going to support this whole range of activities across all the different disciplines and to pull the learning in as well. And then lastly, the public interest, and that's part of the push for open access to data, is that if the government funding, if your tax dollars are part of what's funding this research, shouldn't people have access to it for their own use? Okay. Thank you.